I'm Sanaa Hobeichi from UNSW. So in this talk, I'm going to show how we can integrate climate data, reported drought impacts, and machine learning to improve the identification of impactful droughts that matter to us. First, let's see what typical methods for drought identification do. They consider a precipitation time series, and then they compute a drought index like the Standardized Precipitation Index, or SPI, to transfer the precipitation time series into a new one of standardized values. Then they identify drought events based on that new time series and a threshold. For example, they might say that if we have SPI equals -1 for 3 consecutive months, that's the beginning of a drought. Now here, I gave you an example of drought index based on precipitation, but drought indices can also be driven from another climate variable or a combination of multiple climate variables. And there are several limitations with this approach. First, these climate indices can only analyze a narrow selection of climate variables, but we know that drought results from a complex interaction of multiple climate variables that cannot be ingested in those indices. And also the identified drought events are typically sensitive to the threshold, and there is no consensus in the literature about which threshold we should use. And more importantly, those identified drought events are not ground truth for impact, or in other words, it's not verified whether these are related to conditions that have impact and warrant concern. So why not do better? Here we are suggesting a machine learning approach to improve the drought identification. And with this approach, first we identify past drought events that have documented impacts. Then we examine the climate conditions that happened at the same time. And then we use machine learning to build a damage function that can map those climate conditions to the droughts. And finally, we use the trained model as a drought indicator to identify impactful droughts from climate conditions. And I'm going to go through each of these steps in more details. So we can find drought impacts in many reports, and we can compile a drought database from the reported impacts in those reports. These include like drought impact reports, drought situation reports, climate summaries, and many others. And there's a whole of reported impacts that we can find in these reports. And those impacts will give us the time when a drought happened and the location. So next, we can identify the prevailing climate conditions during those events. And we can build a database similar to this one. Like, for example, in every row here, we can record the location, the observed impact, the year and month, and also the large-scale modes of variability, those ANSO, SAM, and modes of variability that impact drought in that region, and also the local climate conditions related to drought, precipitation, evapotranspiration, and other related variables. And every record can be labeled either as a drought or non-drought. That's because we want to make a database that contains both events, drought and non-drought, so that we can discern between the two. Once we have this database, we can use machine learning to model the relationship between those climate variables and drought. So in that case, all the climate variables will be our predictors, and those labels 1 and 0 will be our target. And we can use tree-based methods because they're very appropriate for this task. They can handle correlated features. They can also capture the combined effect of various climate variables on drought. Among the tree-based algorithm, I use random forest classifier because it's powerful and very easy to implement. Next, once we have that trained model, we can use it to achieve 3 tasks. We can identify droughts by computing the probability of drought occurrence based on the local climate and large-scale modes of variability. We can also analyze the relationship between climate drivers and drought by using tools from interpretable AI. And in particular, we have feature and importance analysis, or another tool called CHAP. And also we can forecast droughts by training random forests to compute the probability of drought occurrence in the future up to 3 months. And we use this approach in Texas, and then we repeated it in Southeast Australia. And I'm going to show some results from both studies. First, in the Texas study, I'll show how random forest performed and how it compares with other commonly used drought indicator. So here we're looking at 3 metrics. True positive, which indicates how many observed droughts were correctly labeled as drought. True negative, which indicates how many observed no drought were correctly labeled as no drought. And false alarm, predicting drought and getting it wrong. Obviously, for the first 2 metrics, the high score is 1, and for the last one, the high score is 0. And we compared it with, so RF is our random forest. AD, PDSI, and SPI are 3 commonly used drought indices based on different climate variables. For SPI, we tested several thresholds, and we put the best results here. And USDM, it's this current state-of-the-art drought index of the US, and it's a blend of several drought indices and experts' input. So it's not automated, but it's now the state-of-the-art index there. Now we have box plots because we tested random forest out sample on different testing data set just to make sure that it's not sensitive to the training data. And we found that random forest outperforms the traditional drought indices, and it performs equally to USDM, so the difference was not statistically different, which was great because random forest was able to provide an alternative drought indicator to USDM while being automated, and it has ability for forecasting, and it can also produce drought information at a higher resolution, unlike USDM. We can also use random forest to generate a drought probability maps and to provide insight into drought development and evolution. So when we applied this approach on the impacted region during the tinderbox drought, so on the left we see the region impacted, and those black dots are where we collected the reports from since 2000. And on the right we see the drought probabilities from year to 2017 to 2020. So we can see that the climate conditions during the 3 winters from 2017 to 2019 indicated a high probability of drought. And we also found that between February 2019 and February 2020, probability of drought was very high, in particular in the times where we had bushfires. We also used feature importance analysis to understand or to find the key drivers of drought for Australia, and also in particular during the tinderbox drought. So in general, we found that Australian droughts are sensitive to large-scale climate drivers, especially ENSO. So here in this graph, we see all the climate predictors that we use to build the model. And on the x-axis, we see the relative importance of each of these predictors. And we can see that ENSO has the highest variable importance, which suggests that it's the most important drivers to drought in Australia. When we repeated the analysis only for year 2019 during the tinderbox drought, we found that the local climate had their importance improved, which suggests that they played the largest role in determining drought probability, while ENSO had its variable importance decreased, which suggested that it was not a dominant driver of drought in Southeast Australia in 2019. So in summary, we can use high-resolution climate and combine it with observed drought impacts to develop a damage function, which was here random forest, that can identify impactful droughts that matter to us. And the trained random forest can compute the probability of drought occurrence, and this is more meaningful than deriving indices which can be interpreted subjectively. And also random forest can be trained to predict the probability of future droughts events. I haven't shown the results here, but we found that when we predicted future droughts, we had a small reduction in performance up to 10%. And also we can use feature importance analysis or other tools from interpretable and explainable AI to identify the key climate drivers contributing to drought conditions. Yeah, that's all for me.